Good afternoon and welcome to our webinar. The purpose of this webinar is to give you a basic overview of standard mechanical presses, including link motion presses and servo mechanical presses, address some of the strengths and weaknesses of each, and compare the two. The ultimate goal is to get you to think about your current applications, your budget, and your possible future needs and determine which press is right for you, regardless of the latest and greatest technology. You know, Stamtec sells both types of presses, so my intent truly is to just help you make the best decision for your particular set of circumstances. And as Randy mentioned, please feel free to ask questions during the presentation via the chat window. You know, I may stop in the presentation to answer that question, but if not, I will definitely take some time at the end of the presentation to address it. So, which press is right for you? Well, press selection depends on a number of variables, but generally, hydraulic press offers more control and versatility, especially in forming. A traditional mechanical press can achieve the highest production speeds, and a mechanical servo press combines control and versatility with higher production speeds. I want to note here that I'm going to talk just a few moments about hydraulic presses, as there are some points about hydraulic presses that are worth mentioning, especially in how they are similar or different than mechanical servo presses and their applications. Hydraulic press generally does not achieve the high cycling speeds, but offers more versatility with its variable stroke length, die space, tonnage, and working energy. Hydraulic press is often the best choice when producing parts with deep, complex forms that require a lot of material flow, or parts that require a long dwell at the bottom of the stroke, including plastics, and when production speed is not as important. You see a couple of photos of some typical straight-side hydraulic press with the long cylinder providing a long stroke. Now, the characteristics of a typical hydraulic press include variable stroke length. If the hydraulic press has a 20-inch stroke, you can use from 0 inches to 20 inches of that stroke as the working stroke because you have full tonnage throughout the stroke, not just at bottom dead center. Control of slide position and motion throughout the stroke, meaning you can start and stop the stroke at any point in the die space and vary the movement at any time and any point in the die space. You can speed up, slow down, dwell, reverse, etc., anywhere within that stroke. Variable slide velocity, even within a single cycle of the press, which is typically configured as fast approach, slow press, and fast return. But again, as noted in the previous slide, the speed can be adjusted at any point depending on how advanced the press controls and hydraulics are in the particular press. Full working energy at any speed. Now this is a big bonus of the hydraulic press, especially when forming, as you can do slow draws, reverses, and dwells to help the material flow better. Full press capacity at any point in the stroke. Again, this means you can have maximum die space usage. For instance, working height and die height, as well as the greatest usage of the working stroke, are all adjustable. Fully adjustable or programmable of all of the above parameters. Now, if you have an old hydraulic press, this may not be the case, but with modern press controls and with some hydraulic press manufacturers actually combining servo motors with hydraulic system. Now, hydraulic presses have more capabilities and flexibility than ever before. So, they have a relatively low initial cost, especially compared to a servo press, but they're usually less expensive than a mechanical press as well. So you might ask, what is the problem with hydraulic presses and why are they not used more in stamping? Well, in reality, they probably could be used more in stamping applications, but there are real limitations that keep hydraulic presses from being more widely utilized. Generally reduced throughput, accuracy, and repeatability compared to a mechanical or servo press. More issues with snap-through, parallelism, and rigidity deflection than a mechanical or servo press. So the reason for this is that hydraulics presses obviously have hydraulic cylinders, not hard mechanical gears and crankshafts. So the cylinders constantly need to adjust for off-center loading, changes in loading across the bed and slide as the parts are stamped and formed, deflection, snap-through, etc. And no, not even super strong gibbing and side frames alone, they will not be enough to compensate for all the potential forces generated in a stamping operation. So these hydraulic system adjustments, which involve electrical signals, transducers, solenoids, hydraulic valve flow and pressure, and so on, they take time and distance, creating inaccuracies within the stroke. And the press, of course, must be slowed down in order to allow time for these changes to take place. It becomes even more challenging with sudden changes such as snap-through, not to mention the havoc being wreaked by vibrations and forces driven back through the hydraulic system. So hydraulic presses have their place, but most often it is not in a true stamping operation. A good example, I know of a customer who recently purchased a large hydraulic transfer press, and they're only able to achieve about 15 strokes per minute, whereas in a similar mechanical press with a similar transfer system, you could get at least 25 strokes a minute. Not to slam hydraulic presses, but the focus of the rest of this will be on mechanical and servo presses, so including link motion and servo mechanical presses. Now, I bet most of you are pretty familiar with standard mechanical presses, but we will do a quick review of mechanical presses now, and then move on to the servo press and link motion press. Well, a traditional mechanical press can achieve the greatest production speeds, especially when running relatively flat parts with simple shallow forming requirements that typically can be processed from coil stock through a progressive or transfer die. And you see here a press we actually have on the floor right now at Stamtec, and it is a small straight side press, 176 ton, and it's got a compact feed line with a combination servo feeder and straightener. You might notice how short this whole press production system is, and I'd be happy to talk to you more about this kind of complete system later. Now, the characteristics of a traditional mechanical press. Fixed stroke length, although variable stroke length presses are available from some manufacturers. In fact, Stamtec makes those, but you have to actually change the cam on the crankshaft to change the stroke length, and this has to be done manually or by a powered mechanism. Kind of a pain and quite an expensive option, so there have not been a lot of these presses manufactured or sold. Variable slide velocity, SPM, but only within a single cycle of the press, of course. Working energy depends on flywheel mass and speed. Most mechanical presses achieve full working energy at the mid-range of the speed range. So in a 20 to 40 SPM press, for instance, full energy is achieved at 30 strokes per minute. Anything below that, the working energy drops off quickly, and you may not have enough energy to get through the work, even if you have plenty of tonnage. Or you may not have enough motor to replenish the flywheel energy in time for the next working stroke. You ever had a press bogged down during a job? Raise your hands. Well, I can't see you, but I'm assuming several of you raised your hands. But this is why. It's actually nothing to do with not having enough tonnage, or the press not having enough tonnage, but rather not having enough working energy. Another characteristic is full press tonnage capacity or rating point only near bottom dead center of the stroke. The rating point is typically 1/8 inch to 1/2 inch off the bottom dead center for a mechanical press. Anything above that rating point in your press's ability to generate and withstand that much tonnage drops off significantly. Tonnage and working energy alone are enough to do a seminar on, but we'll not be able to get into any detail of that here today. However, I or one of our other sales application engineers would be happy to discuss this at any time with you. And really, your best source of information regarding this would come from your die builder. Of course, simplicity of setup and operation. As you know, you pretty much set the die height and the speed and start running parts. Not a lot of complicated settings for the press itself, although, of course, you may use complex feeding and automation systems, die protection, tonnage monitors, and other such things. Typically, the high stroking speeds, as we mentioned. Very high accuracy and repeatability. Everything is hard and mechanical, so you can get it pretty much dead nuts and repeatable pretty easily. Special slide motions such as link motion are available, and of course we're going to be talking about that a little bit more later on. Relatively low initial cost, and I will talk a little more about that later on as well. So the mechanical servo press. Flywheel, clutch, and brake are replaced by high-capacity motors, servo motors. Much of the versatility of a hydraulic press at production speeds often approaching a mechanical press. Stroke, slide, position, and motion, speed, all programmable to allow different combinations to work with a wide variety of dies, part types, and production speeds. So, of course, a servo press is still a mechanical press. A mechanical servo press where flywheel, clutch, and brake are replaced by high-capacity motors. And you see here pictured some of our current models at Stamtec. A small gap-type straight side, then a C-frame press, and a straight side press. And we offer a couple of different versions of servo drive systems for these presses, which I'm going to talk about next. First of all, the basic characteristics of a servo mechanical press. Variable programmable stroke profiles, which include precise control of slide position and motion throughout the range of the stroke. Much like a very advanced hydraulic press, but with much greater speed, accuracy, and flexibility. Variable, precise control slide velocity, even within a single cycle of the press stroke. And then full working energy at any speed. These are all very important parameters, and with servo motors, all these parameters can be controlled very precisely and quickly as compared to hydraulic presses. And of course, you cannot control these with standard mechanical press. So you might call this a drawback, but it really is just a characteristic that you still have with a mechanical press, and the servo press is a mechanical press. Full press tonnage capacity, rating point, only near bottom dead center of stroke. Greater operating cycles than a hydraulic press, in some cases approaching the speed of a mechanical press. You usually still cannot run as fast as a mechanical press because of the limitations on servo motors and drive, for example, heat generation and derating of motors and drives at higher usage. The high accuracy and repeatability, of course, a mechanical press, but with the additional control and accuracy of servo motors. Relatively high initial costs. Now this could be anywhere from about 40% to more than 100% higher than a standard mechanical press, depending on the size, model, specifications, application requirements, etc. So for example, a typical 600-ton mechanical press, which might be around $800,000, could run you $1.2 to $1.8 million for a comparable servo press. So at Stamtec, we offer two types of servo presses, two types of drive systems on our servo presses. Most manufacturers stick to one or the other, but for a few reasons, we offer both types. The first is the link or toggle assisted, cost-effective solution that utilizes standard off-the-shelf AC motors. A link or toggle mechanism coupled with the motors creates a mechanical advantage or mechanical ratios that allow the use of standard motor sizes from proven motor and control suppliers. And you can see there's a diagram of the link motion, and that's one of the types of link motion that we do offer. And it's actually the type of link motion that we offer in this press that you see in the photos. And, the link mechanism is actually the same one as we use in our standard mechanical presses with link motion, but for a different reason. Here it is for the mechanical advantage, enabling us to use the smaller motors. And in the standard mechanical press, it's used to achieve a slide slowdown in the working portion of the stroke. But you can notice here that if you can see in the back of the press there, it's a little bit small, but it's a small servo motor, and you'll notice on the side, the side of the press, there's a small electrical cabinet. So you're able to use the smaller motors and electrical components and cabinets since you have the link-assisted drive. There, that's what I wanted. Okay, so got a pointer now. Some of the advantages of link-assisted servo presses. Cost-effective solution utilizing standard off-the-shelf servo motors. Higher working energy compared to direct drive because of the mechanical advantage supplied by the link mechanism. A couple of disadvantages. And I'm not going to go into a lot of detail today on this. We could do a whole seminar just on the pros and cons of link-assisted versus direct drive servo presses. So I'm just going to touch briefly on a few points. And, I'll be happy to discuss this in more detail with you at a later date, or perhaps we can field a few questions about this at the end of the webinar. Anyway, a couple of the disadvantages of the link-assisted versus the direct drive. Lower tonnage rating point at less distance off bottom compared to the direct drive system. You must use the full stroke length of each cycle. In other words, you do not have a pendulum motion with a link-assisted press where you can shorten the stroke length of the servo press. You can do all the cool things you do with the servo press all the way down to the bottom of the stroke and through the work. But once you pass bottom dead center, you need to go ahead and complete a full cycle or revolution of the press with a link-assisted. Now, the direct drive system, as you can see in the diagram, is you just replace the clutch and brake with a servo motor. And the servo motor drives the pinion gear, which drives the gears. So it's truly just a mechanical press driven by a servo motor without the flywheel, clutch, and brake. So, but for that reason, you have to use much larger, high torque, low RPM motors specifically designed for press applications. And you can see on this press, which is a comparably sized press to the one in the previous photo. This is a 200, the other was 160. Much larger motor in the back, much larger electrical cabinet, which has to stand alone. So those are some other issues to consider. And of course, you're using more energy, electrical energy, to power these items. So some of the advantages quickly of a direct drive servo press. Higher rating point, further off bottom of stroke compared to link assisted. Ability to use shorter stroke length and higher speeds, i.e. pendulum motion. A couple of disadvantages. It employs proprietary, expensive, high torque, low RPM motors specifically designed for press applications. Has lower working energy compared to link assisted systems. Now, although the motors do become special in the large sizes, we do still rely on Siemens, not a proprietary motor manufacturer, for the best in reliability, performance, and availability. So you're not buying a proprietary motor manufacturer when you buy a Stamtec servo press. Now, the working energy on direct drive servo presses is derated when you're running higher speeds in pendulum motion because of heat generation in the drive. So that's kind of an interesting point that I really would not have expected to be the case, but it is. One more thing I want to say about the working energy. You could, of course, you can make the working energy higher on direct drives by increasing, providing larger servo motors, but this can become physically impractical and prohibitively expensive as well. A couple more points to consider. If you're using the pendulum motion, besides just generating a lot of heat in the motors and drives with the constant starting and stopping, you also have the wear, additional wear and tear of constantly starting and stopping the servo motors as you swing it back and forth across the bottom with the short stroke. And one more point about the direct drive, I think the jury is still out on, is the electrical energy consumption. Yes, a servo motor press, a servo press, uses far less energy when it's idle, and the motors are not working, as opposed to a standard mechanical press, which has to keep the flywheel spinning even when the press is idle. But what about the consumption of large servo motors when they are running in a constant production, as we hope our presses will be? That's just some food for thought and further investigation, just how efficient and green, if you will, are the servo presses. Now, I realize I may have seemed to have raised more questions than I've answered, but I hope this will just encourage you to investigate more and think more about your specific situation when you're considering a servo press. Now, regardless of the drive type, servo presses are run by proprietary control programs specifically designed to create the wide variety of possible stroke profiles. And this is the exciting part about servo presses, I think. And I just want to show you a few examples of stroke profiles created by some of our customers for running their specific parts. The compound pressing and forging curve. You can see the part that was made with that curve above it. Deep drawing. Now, I think these curves kind of speak for themselves, as you see how they go quickly down to the work, and then they slowly move through the work and quickly back to the top and back around to the work again. And this perforation blanking mode, of course, goes very quick throughout the entire stroke because it's just doing a perforation in some thin steel, not trying to form anything. Then a warm forming, this one actually does a dwell before it goes into the work, and that's to allow the die to heat up. In this case, it was a magnesium material that you see in that part, and it's a camera case, which when you attempt to do this part cold, the corners crack. But by heating, I think it was 10 seconds it heated in that dwell, and then going through the work and then rapidly getting back out of the work, you still keep high production rates, but you're able to form that part successfully. And then a general forming, and you can see in this curve that you actually pause. It's actually a very fast approach, a shallow draw with a long dwell, and then a fast return. Now I'm going to show you the 9 pre-programmed stroke profiles that we currently use in our direct drive servo presses. And the video you are about to see is of a 440-ton straight side press that we sold about 2 or 3 years ago. But it has the same stroke profiles as the press that we're going to have at Stamtec in Atlanta, which is only 2 weeks from now. And at the show, we're going to be running production on our IS-1200 direct drive 200-ton C-frame servo press. So be sure to come see us if you are going to the show. And what we're about to see in the video are the following profiles: standard crank mode, feeder mode like I just talked about, drawing mode, which we also talked a bit about, fine blanking mode, which the essence of fine blanking is cutting through the steel rather than shearing it. So that's why you see that it goes very slowly through the work to try to create a cut edge instead of a blanked edge or a sheared edge. In die heating mode, which I also spoke about just a moment ago. Pulse mode, this is a mode for like doing an extrusion or a draw as you're going down through the work, backing off a little and then going back through. Forging mode, where you see a little hammer motion at the bottom to forge the part. Coining mode, where you're actually dwelling and staying on bottom, hard on bottom to force the material to flow and move. That's coining mode, which you might see in a forging press, for instance. And then pendulum mode, as we talked about, is so you can run higher speeds, shorter strokes, for instance, in a progressive die. Okay. So I'm going to show you a video now of our SDS servo press, which is a direct drive, straight side, 400-ton press.
2-point direct drive servo press. Integrates the mechanical press and NC servo control system. It's an intelligent, composite, and green product. With servo system, the slide speed can be changed for the hard forming material so as to extend use of the press machine. The linear detecting device assures identical pressing height with bottom dead center rectification system that improves productivity and prolongs the die life. There are 9 built-in pressing modes for different materials. Crank mode. User can adjust running speed. No need of complicated setting. Standard forming jobs like blanking, punching, and bending, etc. are all suitable. Most materials are available for this mode. Coining mode. More than the adjustment in the height of speed change and running speed, it provides the adjustable slide motion stay at the BDC. That offers sufficient forming time, holds the pressure for coining completion, and prevents material springback, often applied like coins and logo coining. Link mode. The speed of forming area can decrease to the lowest to avoid surface cracking from fast stress change in a forming period. The drawing mode is applied in parts drawing, like steel mug and stationary box. Mold heating mode. The main feature is for setting the safety height and time adjustable before reaching BDC. It is developed for hard forming materials like magnesium alloy. The heating in die mode can preheat the magnesium alloy inside the die while longer staying at BDC and form the material slowly, so it can be used in laptop and cell phone cases. Feeder mode. This provides the adjustable stop height and time after passing the BDC. The mode is applied in the automation line of multiple presses integration. Each press has different production processes in the line, and the stamping speeds are different. This mode can synchronize the productions among the press line. Fine blanking mode. For the forming physical specialty, the slide speed can slow down to avoid fracture. It's suitable for forging stainless and high-strength steel. Pulse mode. It provides an up and down pulse curve within the forming area. That makes the slide move up and down again and again to release stress during stamping. In this way, it can deepen the drawing length on the part gradually and increase the yield rate of drawing long and thin parts like lipstick shells and battery cases. Hammer mode. It provides identical height setting for multiple sections and adjustable speed. By repeated hammering process, it can release the inside stress of material and give the material a sleek shape and better mechanical properties. Hardware tools like sleeve, wrench, knife, etc. are all suitable for this mode. Pendulum mode. With the servo control drive, the slide can move back and forth without passing the top dead center. This significantly increases productivity and reduces energy consumption, further providing an eco-friendly working process. The blanking parts like washer, covers, and file holders are all available for this mode.
Now, for all the wonderful things a servo press can do, in the final analysis it still boils down sometimes to a very basic question. Sometimes you don't need all the cool things you can do, or at least potentially do, with a servo press. And it, again, just boils down to a very basic question. How can I successfully make parts faster, but using a slower slide velocity for better quality of parts, less problems with equipment and dies, and within my equipment budget? Well, the answer may be a type of press that's enjoyed popularity over the years, and is now we're seeing a lot more interest in this press again, and in large part, actually, fueled by the recent interest in servo presses. And it is, of course, the standard mechanical press with link motion. This is a press that we recently sold within the last 2 years at a very large manufacturer. And it's an unusual press in that it's 1,100 tons with a 324-inch left to right by only 60-inch front to back bed. And as you see indicated by the model number SL2, it is a 2-point link motion press. And significantly less expensive than a servo press, but does what they need it to do. And of course, it's very fast. So I'd be happy to tell you more details on this press at some other time if you want to ask questions or give us a call later on. So with our link motion drive technology, it's pretty simple. It decreases the slide velocity by up to 40% during the working portion of the stroke, so the material flows more effectively, while the slide velocity increases by an offsetting amount during the non-working portion of the stroke. So you're able to maintain higher production rates. In addition, the slower speed as it goes through the work reduces die impact, punch penetration, snap-through, noise, and vibration, thereby increasing machine and die life. Now you can see that I've listed or pictured 3 types of link motions there. On the left is a Watts-type link mechanism, which we would use on longer stroke, eccentric geared machines, like the one you saw in the previous photo. The second type would be used in a crankshaft type machine with shorter stroke length, and the third type is a knuckle joint, which we would use in our forging presses, corning presses, near net shape, or fine blanking presses. Now these all have slightly different stroke curves, but all have common characteristic of a fast approach, a slow press and or dwell through the work, and then a fast return. And this is all achieved by a simple, very robust, and accurate mechanical link mechanism, without complicated controls or setup. Rather than show you graphic curves of all these, I'm just going to show you some examples using AutoCAD animations and actual videos of presses running. This first animation is just a animation of the link motion that you saw in the large press that I pictured earlier, and you can see how it slows down and actually slows down and even dwells a bit at the bottom of that stroke. You'll see it more so in some other animations and videos that I'm going to show you here in just a second. And this was that basically the same link motion that you just looked at. And this is showing it in a 4-point configuration with plunger guiding. This would be similar to the large press you saw earlier as well, except in this is a 4-point machine. I mentioned knuckle joiner, which is often used in coining and forging presses. This is just a cutaway showing you very slow motion, of course. And you can see that this knuckle joint gets on bottom dead center and just sits there with a hard stop on bottom dead center and dwells for a moment. This is an actual animation of one of our forging presses, a 2-point knuckle joint press, which you don't see a lot of 2-point knuckle joint presses, but we do build them, and you can actually run progressive dies in this as well. I'm going to fast forward this a little bit. As you can see, this is a 2-point knuckle joint, a long dwell on the bottom and a lot of torque right at the bottom there, and it's plunger guided as well. So you've got plunger guiding, 8-point giving, and we build these ultra low deflection and rigidity, ideal for forging and near net shape forming or even fine blanking. See how the link mechanism just operates the knuckle joint. Okay, I want to show you some actual videos of a couple of presses we've sold recently running. This is actually a single point straight side press, pretty much a gap frame press with straight sides, and you can see how slowly it's going through the bottom of that work. Again, a very simple mechanical mechanism, but you get the benefit of very much reduced slide velocity without really reducing your production speeds. Make parts faster, that's what it's all about, right? And with better quality. And this is a 2-point crankshaft type machine. So it has the slightly different type of link mechanism than either the knuckle joint or the eccentric geared machines. But you can see this machine is moving at a pretty good clip, and this is a 600-ton machine. Still got a nice dwell, or not dwell, but a nice slow movement through the working portion of the stroke. And this one's, as I said, running at 50 strokes a minute. And this same press really moving out at 65 strokes a minute. A 600-ton press. Yet that slide velocity is only moving at maybe the equivalent of 40 strokes a minute. The slide velocity through the work. So I would like to thank you for attending this. I hope you picked up something. I mean, the main idea here is to get you thinking and asking questions, hopefully calling us, but if not calling us, calling whoever you need to talk to about your presses. We'd love to see you at Stamtec anytime. We have a 72,000 square foot facility in Manchester, Tennessee, which is only an hour southeast of Nashville and an hour northwest of Chattanooga. In fact, for many of you, you might be on the way to Atlanta for FabTech, and if so, if you're driving, we are 2.5 hours northwest of Atlanta. We're on I-24. So give us a call or drop by anytime you'd like. We'd love to see you and talk to you. And at this point, I will turn it back over to Mike and to see if we have any questions.
Okay, thank you very much, sir. And ladies and gentlemen, if you'd like to ask your question over the phone, you may press *1 on your telephone keypad at this time. Once again, that is *1 if you'd like to ask your question over the phone. Of course, you can continue to submit your questions through the chat box on the bottom left-hand corner of the screen. Just simply click on the private tab and then select Leaders and Assistants and type your message into the box. And please hold while we poll for your questions. And we currently have no questions through the phone. How about the web?
Nothing just through the chat just yet. Lee, did you have a couple that did come in during the presentation?
No, hopefully this is because I answered everybody's questions. But it's really hard to condense this down into less than an hour, and without really getting long-winded, and also, but you're still also not able to cover everything. I hope I effectively covered what we wanted to talk about today. And if anyone has any questions at all, they're always welcome to call me at Stamtec or email me, and you've got the information right there on the screen. And that said, I think we're done for today.